Hi everyone, thanks for joining us for this practical overview of the PrototypeML platform, an advanced researcher and practitioner guided tutorial implementation of U²NET, a recent state-of-the-art salient object detection paper. We encourage you to open the project and explore the PrototypeML platform for yourself during the course of this video. Now we'll show you how to use the PrototypeML platform. We'll go over the Model Designer interface, how to add third-party components or libraries from the component repository, and how to create blocks and mutators, and accompanying concepts such as ports and parameters. So let's get started. The interface is split up into three main sections. On the left-hand side is where you'll navigate your components, add new components such as blocks, mutators, or add third-party components or libraries from the package repository. You'll also be able to search your components very easily and download your code at the end of your project. The middle column is where you'll edit your blocks and mutators, while the right-hand side is where you're going to edit various properties. So let's start by adding the PyTorch library as a project dependency. This gives us access to all of PyTorch's layers and functions. Click Add Package Dependency, go ahead and click on PyTorch, and click Use to add it to your project. Now within the packages directory, you'll see that we now have PyTorch as an option. And within PyTorch, you'll find all of PyTorch functionality. Now let's create our first neural network. Let's start by creating a block, the visual equivalent of a PyTorch neural network module class. Click Add, click Block, give the block a name, let's call it Test Block, and click OK. We can open the block simply by clicking on it. Welcome to the block editor, where you can visually design your neural network. The main section shows a visual graph of your neural network design, to which you can drag and drop neural network layers from the left sidebar to add them to the graph and connect them into arbitrarily complex architectures. The Properties bar on the right-hand side shows various block settings and configurations, such as ports and parameters. We'll get more into depth with these later. The first thing to notice about the block editor is that every block consists of an input node and an output node. These represent the input to and the output from the PyTorch neural network module. Every node within the block represents its inputs and outputs via ports, visually indicated by the round circles found at the top and bottom of nodes. Let's go ahead and build a basic convolutional neural network. First, let's find the 2D convolution layer inside the PyTorch library. We can add this layer to our block by simply dragging and dropping this layer from the component sidebar into our block. While we're at it, let's add a max pool and a relu. Let's use the search functionality. Max pool 2D and relu. Excellent. Now we have all the components necessary to build our basic convolutional neural network. So how do we connect these components together? By clicking and dragging from any port to another port, we can create a link connecting the output and the input between the two nodes as shown. Let's connect the rest of our components. Links also allow us to visually represent more complicated interaction between nodes, such as skip connections, simply and easily. Let's add a skip connection between the input and the output. By clicking on the input port where the two links meet, we can choose how we want the two outputs to be combined and in what order. So now you've learned how to add components to your blocks and link them together in powerful ways, completely visually. Let's get back to basics. You can go ahead and click the Format Graph on the right-hand side to very nicely visually format your graph. So now that we have the components of our neural network linked together, you might be wondering how you can edit the parameters such as the kernel size or stride of the convolution. By clicking on any node, the Properties bar will switch to show that component's properties and parameters, which you can easily edit. The instance name represents the variable name of the layer. The Repeats field allows you to quickly repeat the block a variable number of times, assuming the input and output shapes are compatible. The Apply Activation field provides you with quick access to common activation functions. Below, you will find all the various parameters you can edit for this specific component. PrototypeML supports complex parameter creation and passing, which we'll get back to later. To return to the block properties, click anywhere else on the graph. As previously noted, ports represent the inputs and outputs of a component. By default, components contain one input port and one output port. If, say, we wanted to pass two inputs to a component, we could add an additional port. You'll now notice that the input node on the graph now reflects the newly added input. While ports represent the tensor data going in and out of components, the PrototypeML parameter system allows for properties to be passed between components as well. Let's say the stride of the convolution should be configurable, rather than hard-coded. Let's add a parameter for stride. You can see our newly created parameter. Now let's change the convolution to use the passed-in stride parameter rather than the hard-coded default. When editing a component parameter, you'll notice if there are any other parameters on the block that we can pass down to this component. Let's go ahead and delete the 1 and put in stride instead. The convolution, stride, will now be set to the pass stride defined by the block. So now we've added our components, defined how they connect, and even added some extra parameters and ports. We can see the code produced by this block at any time by clicking the Toggle Code View button on the right-hand side of the editor. As you can see, by traversing the block component graph, PrototypeML is able to generate clean, complete, and functional code automatically. Now let's dive a little deeper into the system. Blocks allow us to visually define neural networks, and either blocks or mutators can be added to a block from the component sidebar. Mutators are the second primary component of the PrototypeML platform, and allow us to encapsulate specific pieces of functionality so that they can be modularly used within the block editor while giving us complete control over functionality. Let's go ahead and have a look at the convolution 2D mutator. The mutator editor consists of several distinct code editors, each with a specific purpose, while the property sidebar displays a view similar to that of the block, with ports and parameters. Through the use of magic variables displayed in curly braces, such as highlighted, PrototypeML allows you to code complex functionality that can be reused throughout the platform. As you can see, the convolutional layer usage is separated into several components. First, the torch library itself is imported within imports. Then, the convolution is initialized in the init code block with the instance variable and params variable. When used, the instance variable will be replaced with the name of the instance as defined, and the param variable will be replaced with a formatted parameter string. Third, in the forward section, the output port variable is set to the output of the layer's forward call, which receives the input port as a parameter, and is then executed. While more convoluted than the blocks to explain, these magic variables provide users with a powerful API for integrating their components with the PrototypeML platform, and are easy to use. While not necessary for a beginner, familiarity with mutator design can be beneficial. Finally, ports and parameters can be defined just as they are with blocks. So now hopefully you're a little more familiar with the PrototypeML interface, how to create blocks, how to add components to blocks, how to connect components together within blocks, how to add ports and parameters, and how to view the code when you're done creating a project. Alright, so now we're going to switch gears, and I'll guide you through the creation of an object saliency model described in the recent paper U²net, going deeper with nested U structure for salient object detection that was published in Pattern Recognition 2020. The goal of salient object detection is to segment the most visually prominent object in an image, as shown. The results of this paper are extremely impressive, achieving state-of-the-art results across several benchmarks and winning 6th place in the medical MICCAI 2020 Malignant Thyroid Detection Competition. It has also been used in some neat applications, such as the following augmented reality copy and paste app. The architecture of this network is similar to that of a unit segmentation network on steroids. It is constructed from multiple nested levels of residual U blocks connected together in U shape to perform multi-scale intrastage and multi-level intrastage feature extraction. Specifically, it consists of a 6-stage encoder, a 5-stage decoder, and a saliency map fusion module. We are going to review the implementation of this fantastic network in PrototypeML. This took around 3/4 of an hour or so to construct from scratch. You're invited to open the project, follow along, and are specifically encouraged to actively build the smallest of the residual U blocks with us so you can try PrototypeML out for yourself. The implementation pictured is visually very similar to the graph presented in the U² paper. We have the 6-stage encoder, we have the 5-stage decoder, and we have the saliency map fusion module. As described in the paper, there are exactly 7 outputs from this network. And every upsample and downsample stage here is an instance of a residual U block containing a very similar looking unit within. The numbers on the RSU blocks, as pictured, numbers 4 to 7, define their height as configured according to the spatial resolution of the input feature maps. Stage 5 and 6 do not further downsample, as it results in a loss of context. So let's dive into building the smallest residual U block. First, we've gone ahead and built most of the blocks you'll need to complete the network. We'll go over those briefly. First up is the most basic convolution sequence. Next, we use the basic convolution block and a max pool to downsample the input. Additionally, we pass the conv to the output directly in addition to the max pool so that we can use it later in our skip connections. Next, let's have a look at the upsampling. Compared with the 2 outputs of the downsampling, the upsampling receives 2 inputs, one which it passes through a convolution, and the other whose shape it uses to correctly upsample the input to the right size. Finally, we get to the smallest residual block, which we will build together. Let us begin by dragging in the components we require. First, we need an input convolution layer that transforms the input feature map to an intermediate map. Second, we need to create a symmetric encoder-decoder with a height of 4 that takes the intermediate feature map and extracts and encodes the multi-scale contextual information. We'll start with the downsamples. And let's rename the blocks as we go. We'll use the duplicate instance instead of dragging it in from the side. Similar to the main portion of the U-squared network, the third and fourth down convolutions don't want to also downsample. Now we'll add the upsamples. Notice how we're creating this U-like structure. Now we'll add the skip connections. Since the second output port of the downsamples provides the shape to which we want to upsample, we'll connect those as well. Now let's go ahead and clean up and rename. Now let's add the parameters. The first convolution receives in channels and should output out channels. The first downsample receives out channels and should output mid channels. The second downsample should receive mid channels and output mid channels. Third block should receive mid channels, output mid channels, and the fourth should receive mid channels, output mid channels, and have a dilation of 2. Now let's do the upsamples. Should output mid channels. Second one should also output mid channels. Finally, the last block here should receive mid channels times 2 and output out channels. Now let's make sure that all these concatenations are concatenating on the first dimension. Excellent. Finally, we'll add a residual connection by drawing a skip connection from the output of that to the input of here. And we'll make sure that that's an add. And there we have it, the complete implementation for the residual UNet block with a height of 4. I encourage you to pause for a moment, inspect the parameters, inspect the inputs and outputs of the various different components in this graph, and go ahead and look at the code. As we've implemented all of the remaining residual blocks of varying heights, RSU4, RSU4F, which uses dilations, RSU5, 6, and 7, this network is now entirely complete. You can go ahead and download your code, open it up, extract it, and I encourage you to train and test the model. The results really are quite impressive. This concludes our tutorial on the U-squared net. Hopefully you now have a familiarity with the PrototypeML interface and functionality. We encourage you to read our documentation and check out our other videos on the advanced functionality we haven't covered in this video. If you have any questions, please don't hesitate to get in touch. Thanks for joining us today.